surgery. So I hope that we will be able to finish them all today so that we can start the instruments tomorrow, inshallah. Okay, starting with the intraocular lenses. Usually there are one or two questions in the exam about the intraocular lenses. So let's start the journey of the intraocular lens with why did we invent the intraocular lenses? So before the era of the intraocular lens, which we will be talking about the middle of the last century, after cataract extraction, they used it to correct the refractive error with glasses or with contact lenses. But there were problems regarding the glasses that we have mentioned them or have mentioned most of them before, like the prismatic effect of the thick lenses, of thick plus lenses. You remember when we were talking about the aphakia, we said that the glasses will have a prismatic effect and ring scotoma due to the thick lens. And also there will be marked constriction of the visual field, as they will cause the pincushion distortion of the visual field, and there will be lack of stereopsis, as the patient will not be able to fuse both images from both eyes. And of course there will be some sort of spherical aberrations caused again by the prismatic effect of the lenses, and false orientation. As we said, the high plus lens will cause the objects to appear more closer to the eye than they are really. So from this perspective, a great need for an invention for the intraocular lens have arisen to overcome these problems. So when did this issue all start? It was started just after the World War II. So after World War II, they discovered that the pilots who undergone trauma from the glasses or that were used to manufacture the glasses of the window shield of the plane of the warplanes. When they get trauma with these glasses, they were not antigenic, so it didn't provoke any inflammatory reaction in the eye. So they knew that this material is not antigenic to the eye, which was the polymethyl methacrylate, and hence they thought of making some intraocular lenses inside the eye from the same material. Several forms of the IOL coexist now. So we have the monofocal, which will correct only for the distance, and we have the toric intraocular lens, which will correct for both spherical and the cylindrical error. We have the multifocal, which will correct for near and far, and as well as the accommodative IOL, but will be just by two different mechanisms. And we have the phakic IOLs that can be added to the normal crystalline lens inside the eye to compensate for larger refractive error, specifically for myopia. So if there is high myopia that is beyond the margins of laser vision correction, then the phakic IOL will be the suitable option here. So just before the advent of the intraocular lens, or with the advent of the intraocular lens, there was an alarming question here. How can we calculate the power of this intraocular lens? The power, or the calculation of the power of the intraocular lens, will be subjected to many factors or to many variables that will determine the power of the intraocular lens. First of all, and one of the most important, will be the axial length. Then we have the corneal power. And there was a new term that is called effective lens position, which is the position of the lens in relation to the iris and in relation to the retina, which will be, in some equations, will be corresponding to the anterior chamber depth in the early equations or in the early formulas. And finally, there is a constant which will be different according to the IOL material and design. So this is called an A constant. By combining these factors together in formulas, this will result in what's called IOL formulas. And these IOL formulas will result in the power of the intraocular lens. So what are these formulas and what was the evolution of these formulas? Before the evolvement of the formulas, there was a historical method that was used in the start to calculate the power of the intraocular lens. So this was like the initial method. This method proposed that the power of the intraocular lens would be equal 18 plus 1.25 multiplied by the refraction of the patient. So for example, if the patient is myope -1, then we will add +8 minus 1.25. And if the patient is hypermetrope, so the final IOL power will be 18 plus 1.25. So the IOL power will be plus 19.25. So this is like an empirical method for measurement of the intraocular lens, assuming that the patient who have myopia will need less power and the patient who have hypermetropia will need more power. And you can imagine, or you can think that this power or this formula is not an accurate formula at all, because as you say, there will be an error of more than 1 diopter over 50% of patients. And this is expected because the formulas didn't take into consideration many factors that will affect the IOL power. So there have been large errors that caused by difficulty to determining the patient's refractive error. So at that time, they didn't have an autoref, they didn't have retinoscopy, so they didn't have any clue about the patient refractive error. Also, another problem was the nuclear cataract. As we know that the nuclear cataract can cause myopic shift, so it can cause an index myopia. But this index myopia doesn't have any relation to the actual increase of the axial length of the eye or actual increase of the refractive power of the eye. So this will cause like increasing the myopia, but without actual elongation or actual increase in the overall power of the eye, and this will lead to again false results after this equation. So from here was the initial start for the preparation or for formulation of intraocular lens formulas. So the first generation that were used or that was used to calculate the power of the intraocular lens is called the first generation. And the first generation will be consisting of 2 types of formulas. The first type will be called theoretical formulas, and the second type will be called regression formulas. So what was the basis? In the intraocular lens formulas in the first generation, the effective lens position was constant. This is very important. So every intraocular lens will assume that the effective lens position is 4 millimeters. As at that time, the intraocular lens were only implanted in the bag or in front of the iris. So there were no intraocular lenses that were implanted behind the bag or in the bag. So they assume that the effective lens position is 4 millimeters. And in the theoretical formulas, this was called an anterior chamber depth. So the anterior chamber depth will be the same like effective lens position, which was a constant value. And hence the inaccuracy of this formula, because as you all know that anterior chamber depth is not the same in all patients or in all individuals. So this formula proposed that it is fixed and so that it will not be an accurate formula. So what are the types? First of all, the theoretical formula. And by saying theoretical formula, it is based on a theoretical eye, which is the Goldstrand eye. You remember the schematic eye of Goldstrand that make a schematic representation of the power of the eye by calculation of the power of different refractive media of the eye, which are specifically the 2 systems, which will be the cornea and the lens. And since we remove the lens by the cataract extraction, the second refractive medium will be intraocular lens. So based on the Goldstrand eye, assuming that the eye has about 60 diopter of power, and we know the power of the cornea, so we can calculate the power of the intraocular lens. But in this case, there are different factors that were that they were theoretical, or they didn't have an actual estimation of these factors. For example, the refractive index of the cornea and the effective lens position, or what sometimes it's called the estimated lens position, and the distance of from the intraocular lens to the retina. As I told you, it was in the anterior chamber. So these factors have been just were put theoretically without any proof of their actual values. So as you may expect, that these formulas were not that accurate. So, but it has a great value, because after doing thousands and thousands of cataract surgeries, and we now have patients who put intraocular lenses in their eyes, whether they are accurate or not, but we have a very large database. This large database can be now utilized in order to form what is called the regression formulas. So just before going to the regression formulas, just an example for the theoretical formulas is called the Bankhorst formula. The Bankhorst formula, it is using the previous mentioned factors, and it is used a correction factor for the surgically inducing corneal flattening. So, for example, the corneal incision will cause corneal flattening. So, in order to compensate for this, this formula used the refractive index of 1.333 instead of 1.336, so that we can increase the corneal power by 0.5 diopter, so that this will compensate for the corneal flattening that is made by the incision. So this is just a way how can we theoretically compensate for the IOL power using one factor, which is the refractive index of the cornea. As I said to you earlier, that from many patients that underwent the refractive the cataract surgery and intraocular lens implantation, we have now a very large database of these patients. So by putting the data from these patients into the computer and analyzing these data, we can now know what did go wrong. So we know what was the problem. Is the problem in the power of the K reading, or it is the power of the axial length, or what was the problem? So just we put the data of the thousands of operations inside the computer and analyzing the preoperative data, and then ask the computer if the patient who has an A K reading and has B axial length, and then he has power of C, which is the power of the intraocular lens, and then he had D of postoperative refractive error, and this D is not 0. So how can we reach 0? Please, computer, analyze these factors and tell me what should be the proper intraocular lens power. So after analyzing this, please tell me what should be the axial length and what should be the K reading in order to reach this optimum intraocular lens power. So the computer performed the statistics and now can now derive a mathematical equation that utilize different factors in order to reach the correct intraocular lens power. So the most famous one of this regression formulas was the SRK formula. So the SRK formula is named after those who invented it, who were the Sander and Retzlaff and Kraft. These three scientists make their equations and now put a formula that is using different factors in order to calculate the power of the intraocular lens, which was the first real attempt to reach a good formula for the intraocular lens calculation. In this formula, the power of the intraocular lens needed for reaching the emetropia will be equal a constant named A constant, which will be different according to the material of the lens, minus 2.5 multiplied by the axial length, minus 0.9 multiplied by the average K reading. Again, the power of the lens will be equal A constant minus 2.5 multiplied by the axial length minus 0.9 multiplied by the average Q reading. So from this equation, we had a great piece of information that the difference in the axial length or miscalculation of the axial length will form or will result in great mismatch in the IOL power, because it will be multiplied by 2.5. On the other hand, the Q reading, if there is miscalculation of the Q reading, it will result only on 0.9 difference in the power. So since the axial length is measured in millimeters, so 1 millimeter difference in the axial length from the true axial length will result in about 2.5 diopters difference in the power of the resultant IOL. Likewise, the 0.9 or 1 diopter difference in the Q reading will result in 0.9 diopter difference in the power of the resultant intraocular lens. After doing the first generation formulas, it was found that it was good and efficient for those who have average axial length. So it will be good for those who have 22, 23 axial length, but it wasn't that efficient in case of very short eyes and very long eyes. So what was the problem? The problem is that the intraocular lens position will be different according to the axial length of the eye. So the effective lens position wasn't taken into consideration in the first generation formulas. That's why the second generation formulas thought to put into consideration the effective lens position. So the anterior chamber depth is now no longer constant in all eyes, but it will be variable with the axial length. So the evolution of the SRK2 formulas now was done in order to modify the SRK, the original SRK formula. So it was based on the same original SRK formula, but in this condition, the A constant will be variable. How can we change the A constant to reflect the changes in the effective lens position? This can be done if the A constant will be the same like the original SRK formula if the axial length is between 22 to 24.5. But if the axial length is decreasing, then we will need to increase the A constant by 1 or 2 or 3 to reflect the decrease of the axial length, so that it will be decreasing in the effective lens position. On the other hand, if there is myopia, so there will be high axial length, then we need to subtract 0.5 from the A constant in order to have to take into consideration the anterior chamber depth and the effective lens position. After this, there was a new generation of the IOL formulas. It's called the third generation formulas. And the third generation formulas have taken more depth inside the effective lens position. So in this formulas or in this generation, the effective lens position is not only based on the axial length, like the second generation, but it also takes into consideration the corneal curvature. So in the third generation IOL formulas, it is based on two factors: the axial length and the corneal curvature. So they were more accurate than the theoretical formulas, and they were also more accurate than SRK2. Examples of the third generation are the SRKT. So the SRKT, remember T for tall, because they are used for very long eyes. So if their axial length is more than 26 millimeters, then these formulas will be of the choice. Then we have the Holiday one, And the Holiday one can be used for long eyes between 24 to 26 millimeters. And the Hover Q formulas are used for short eyes less than 22 millimeters. So these are the formulas representing the third generation, and they are now can be used according to the axial length of the eye. So whether you should first know what is the axial length of the eye in order to know what is the suitable formula to use. So did we stop here? The answer is no, because there is another fourth generation. And the fourth generation have taken more insight into the effective lens position. So it didn't they are not satisfied by only two variables, but they need more variables to determine the effective lens position. Why all this care about the effective lens position? Because we said in the previous lecture that the lens position will determine the effective power. So the more the anterior the lens, the more the power, and the more posterior the lens, the less the power. So if the lens is not in the accurate position, this will result in post-operative refractive surprise and post-operative refractive error. So we need to calculate the effective lens position accurately in order to have an accurate biometry. So what are the formulas that are representing the fourth generation here? It will be the Holiday 2, and the Holiday 2 doesn't only takes into consideration the axial length and the key reading, but also the corneal white-to-white measurement. So the white-to-white measurement will be basically the space or the distance from limbus to limbus, or the corneal diameter, and also the preoperative anterior chamber depth and the phakic lens thickness, or the crystalline lens thickness, and the patient age and sex, because there will be changes in the anterior chamber volume over the age and over the sex. As you know, the anterior chamber, it will be shallower in females than males. This should be taken into consideration with the axial length and the key reading. So these are the result of the Holiday 2. It doesn't only take into two variables, but also other variables in order to formulate a calculation power formula for the intraocular lens. The other form or the other type of the intraocular lens will be the formulas for the fourth generation will be the Haig's formula. In the Haig's formula, it will eliminate the K reading as a prediction factor and replace it with the preoperative anterior chamber measurement. So the K reading here is no longer a factor, or the preoperative K reading is no longer a factor in determination of the power of the intraocular lens. And this has a particular importance in patients who have undergone refractive or corneal refractive surgery. For example, if a patient who had LASIK, and this if the patient had LASIK, then there will be change in the post-operative K readings. And in this condition, if this patient will undergo cataract surgery afterwards, this will lead to a wrong calculation of the power. But since the Haig's formulas doesn't take into consideration the preoperative K reading, so this will be the most suitable formula from all these formulas in order to calculate the power of the. No, it is not accurate enough. I'm just saying that will be the most accurate in all these formulas, but to be more accurate, it is better to use the online calculators by the ASCRS, or the American Society of Cataract and Refractive Surgery. So you just type in the Google the online calculators of intraocular lens of the ASCRS, and you will find that there are different pages and different online calculators that are used for different refractive situations, for myopia, for hyperopia, and they will require you to enter some data regarding the patients, and then they will calculate the power for the intraocular lens. But just on this scope of the optics, we are talking that the Haig's formula will be the most accurate among all other formulas. Then after knowing what are the different formulas that will be required or will be suitable for measuring the intraocular lens, let's now discuss what are the individual factors that will control the power of the intraocular lens. According to the SRK formulas, we said that there will be an A constant and this will not be changeable. And we have other two variables, which will be the K reading and the axial length. Measurement of the K readings will be discussed thoroughly in the instruments by discussing the keratometers and other instruments. So here we will come to the discussion or how to measure the axial length. We have two methods in order to measure the axial length. It can be done by either the ultrasound, and if we are measuring the axial length in order to obtain the IOL power calculation, this process is called biometry. So ultrasound biometry is the one method for measurement of the axial length, and the other method will be the laser coherence interferometry. So what will be the major difference between the laser and the ultrasound? Axial length measurement is based on determination of how far is the cornea from the retina, or how is the length of the eye. So we don't just take a ruler inside the eye and measure it by millimeters, but we induce something that will enter inside the eye and bounce back. And when it reflects from the surface of the retina, we can know what is the distance that it traveled inside the eye, and by knowing the distance, we know what is the length of the eye. So this something or this thing that we propagate inside the eye can be just an ultrasonic waves, or it can be an infrared rays. So whether we are using the ultrasound waves or the infrared rays in order to know what is the distance of the eye and what is the length of the eye, both of them can be used for the axial length measurement. Different methods can be used for ultrasound biometry, like immersion technique and the contact technique. And there are different devices that use the laser coherence interferometry principle for measurement of the axial length, like IOL Master and LensStar. So what is the basis of the ultrasound biometry or the A-scan? By placing a probe of it's called piezoelectric crystals that will vibrate, and these vibrations will emit ultrasonic waves that will enter inside the eye, travel along the different media of the eye, and then reflect back. And then after they reflect back, it is received through the same probe that will transmit the signals in the an attached screen, giving an overview of the reflectivity, or what's called the sonography of the eye, or how much every structure inside the eye is either hyperdense or hypodense or isodense. So the different media of the eye will give high reflectivity. As you can see here, this is the first one, will be the probe. Then the second spike will be the cornea. Then there will be two spikes representing the anterior and posterior surface of the lens. Then there will be long space representing the vitreous. And then there will be a spike for the retina and spike for the sclera. Then later on, the spikes will decrease, representing the orbital fat. So if we have the different ocular surfaces that will be hit by the ultrasound are of the same length, so we know that we are perpendicular over the surface of the eye, and then we will have as an accurate measurement of the axial length starting from the cornea till the retina. So this will be the technique. What will be the modalities of measurement of the biometry? The first one will be the contact method. And in contact method, we place the ultrasound probe over the eye directly. So the ultrasound probe is placed over the central part of the cornea, which will emit the there will be a targeting beam, infrared beam, so that the patient can look at it. And then this probe will emit ultrasound waves that will reflect back from the cornea, and then it will manifest as in the screen. Here we have a great problem that sometimes if the examiner is not oriented with the position of the probe, this probe can indent the surface of the cornea. So assume that this is the globe and this is the cornea and this is the probe. So the probe should be just touching the cornea. But what happens if it is more indenting? If it is more indenting the cornea, this will result in artificial decrease of the axial length of the eye. So in order to compensate for this decrease of the axial length, the resultant power of the IOL will be high. So there will be overestimation of the intraocular lens power. And this will be the problem with the contact technique of the eye scan. And of course, if the eye is shorter, this will lead to more effect or more amplification of this indentation problem. So this will not be the best method for measurement of the axial length of the eye. But there is another method which will negate the effect of the probe over the surface of the eye, which is called the immersion technique. The immersion technique in which we place the probe inside a cup filled with saline. This cup filled with saline will be put over the eye so that there will be no direct contact between the cornea and the probe. And the sense that the probe will emit its ultrasound waves, it will hit the water first, then it will enter inside the eye and then will reflect back. So it will be better reflecting of the axial length, and in some studies it is comparable to the IOL master. So it will avoid the effect of the shortening or induce the shortening of the eye caused by the contact. And it was reported that this artificial shortening can cause about 0.25 to 0.3, which will result in about 1 diopter of calculation power of the intraocular lens. After this, in 1999, a new instrument have been developed by Carl Zeiss, which is called the IOL Master. The IOL Master have made the process of biometry very easy and very handy. This can be done by using the laser coherent interferometry. So this laser coherent interferometry utilizes an infrared rays that will enter inside the patient's eye, hit the retina, and reflect back, and hence it can now measure the axial length of the eye. Not only the axial length of the eye that can be measured by this device, but also other factors like corneal power or Kerr reading, anterior chamber depth, and the corneal wide-to-wide diameter. So this device, this all-in-one device, can use this only device can be used for measurement of the biometry without need of any other devices. And so this device can measure the Kerr reading, can measure the axial length, and even it has a software that can calculate the IOL power. So it can use the third and the fourth generation formulas in order to calculate the resultant intraocular lens power. The only drawback of this device is that, as we mentioned, it uses an infrared rays. So that if the patient has opaque medium, for example, if he has dense posterior subcapsular cataract, or if they have mature cataract, then these patients, the infrared rays will not be able to enter inside the eye, and then it will not be able to calculate the axial length of the eye. It can measure the other measurements, but it cannot represent, or it cannot predict what is the axial length of the eye. So it will not be suitable here, and the only alternative or the only solution here will be to do the ultrasound. So we do the ultrasound, and then we put the IOL, the axial length obtained from the ultrasound inside the IOL master. And by putting the IOL, the axial length from the ultrasound, and by obtaining the Kerr reading from the IOL master, we can now calculate the power of the intraocular lens. Or, of course, if the patient is unable to fixate, for example, if the patient has nystagmus then this will not be suitable for measurement through the IOL master. Another device that was introduced with the same principle is the Hagstreit lens star. So this device uses the same principle of the laser coherence interferometry to measure the axial length of the eye and to measure the IOL power. So this is everything about the IOL power calculation. Let's now move to the other types of the intraocular lenses, like the multifocal and the accommodative IOL. As we said in the last lecture, the multifocal are just simply lenses that can see the near and far. So what was the evolution of the multifocal intraocular lenses? They started by the same way like the multifocal glasses. So they started by split bifocal, by making an intraocular lens, that this intraocular lens is split to two halves. One half will be for near and the other half will be for far. So half of the optic will be for near and the half of the optic will be for far. And in case of the near segment, it will have an extra power or an extra plus power in order to see for the near. And this power will not be affected by the axial length or the corneal power, but it is affected by the effective lens position. And this design will be independent of the pupil size. So whether the pupil is large or small, this will not make any difference because the split is in the half. So whether there is a small pupil, moderate sized pupil, large pupil, they will be all the same effect. Then the next generation was the multiple zone intraocular lenses. So the multiple zone intraocular lens will take into consideration the pupil size. So the intraocular lens will have three zones: a central one, and the peripheral one, and an annulus in between. So the central one and the peripheral one will be accounting for the distance vision. So if the pupil will be very narrow or it will be very large, then the patient will be able to see clearly the distant vision. While the middle annulus zone, this middle annulus zone will be accounting for the near vision. So in order for the patient to see for the near, they have their pupil to be moderately small pupil. So moderately small pupil will be if the patient has moderately small pupil, then they will be seeing the near targets. If they have very small or very large pupil, they will be seeing the near target, the far targets. Another design for multiple zone intraocular lens will not divide the intraocular lens for three zones, but into several zones. As you can see here, it will be different zones, and these different zones will be variable in the power range of about 3 to 5 diopters. So there will be change in the power zone from the center to periphery, as you can see here. So what is the advantage of this design? That doesn't take into, or the pupil of the side of the pupil doesn't matter anymore here. So whether it is small or large, or whether it is oval or it is rounded, whether it is central or ectopic, then the patient will be able to see all distances, whether the near or the far. Another design of the multifocal intraocular lens is called the diffractive IOL. The diffractive intraocular lens will be have a Fresnel diffraction optics. So you remember when we were talking about the Fresnel lenses. So these Fresnel lenses will be sculpted or will be designed over the surface of this intraocular lens. So this lens has a specific configuration, which is frequently asked in the exam. The refractive surface, which is responsible for the distant vision, will be constructed in the anterior surface of the lens. Again, the anterior surface of the lens will carry on the refractive power of the lens, which will be responsible for the distant vision. However, the posterior surface of the lens, it will have the Fresnel configuration. So this Fresnel configuration, which will be called the diffractive surface, will be on the back of the intraocular lens, which is then will produce a second image, as this image will have, or this configuration will make the second image or of larger power, so that it will be accounting for the near vision. So the patient used the anterior surface for the distant vision, and the posterior surface will be used for the near vision, as it has an effective add or plus add power. So what is the problem of the multifocal intraocular lens? We can divide them into three problems. The first problem is a problem of the patient. The second problem will be a problem of the surgeon. The third problem will be the problem of the intraocular lens itself. The first problem of the patient is his brain, because his brain should be trained to see two images and neglect one image. So when the patient will see two images at all the times, so he may complain of diplopia and may complain of eye strain. So in order to compensate for this two images, which is for near and for far, his brain will try to neglect one image in order to see the second image more clearly. Some patients will be able to do this, but others cannot do this. So it is a very variable factor here. So again, the first problem of these lenses is the adaptation by the patient. The second problem will be a problem of the surgeon. So if the surgeon didn't center the intraocular lens clearly in the to center the intraocular lens perfectly in the surgery, this will result in decentration. And in case of decentration, the patient will not be able to tolerate it. So if the visual axis doesn't pass into the center of the lens, the patient will complain of different problems like halos, like glare, like diplopia, like the appearance of ghost images. So there will be an image of the object with a blurred image beside it, and decreased contrast sensitivity. The fourth problem is the problems of the intraocular lens design itself. So there was a famous study that compared the intraocular lens to the single focal lens or the monofocal lens to the multifocal lens, and they compared that difference. They compared different factors like contrast sensitivity, like the diplopia, like the quality of the image between both of them, and it was found that the multifocal lens have poor quality of vision and poor contrast sensitivity, and more incidence of monocular diplopia, because the patient is seeing the two images and not a single image. So they have two different foci. And also they will have poor night vision problems. So these patients, they shouldn't take this lenses if they have any problems within the retina, like macular disease. So these are the disadvantages that are associated with the multifocal intraocular lens. Other forms of the intraocular lens will be the accommodative intraocular lens. The accommodative intraocular lens will be based on a principle is to instead of having an intraocular lens that will see the near and far, why not we put two intraocular lens, that one will focus for the distant and one for focus for the near. So there were two main designs for the accommodative IOL. The first one will be called the dual optic. So we put the two intraocular lenses inside the eye, so that one will focus for the distant and the other will focus for the near targets. So the fovea here will receive the two different images. And again, it should learn how to neglect one image and to receive the other one. Different designs have been manufactured. Therefore, we have the dual flex. And in dual flex, we have two, the intraocular lens will be one inserted in the bag, which will be responsible for 2/3 of the total power of the refractive error. And the other one will be implanted into the ciliary sulcus and will account for 1/3 of the refractive power. So this is called the dual flex. A dual optic system, it is a single lens that has two surfaces. The anterior lens and the anterior optic will be a plus power, and posterior optic will have a minus power, and there will be haptic that will combine both of them. So it's like a complex intraocular lens that has anterior optic, which will be carry a plus power, and posterior optic, which will carry a minus lens power. So by combination of both of them, there will be the patient can see the distant target and the near target. Piggyback intraocular lens will be by putting two intraocular lens in the posterior chamber. So these will put by inserting single IOL in the first instance or in the first surgery. Then after 1 month, there will be another intraocular lens that will be in front of the original one. But we need to make sure that the posterior lens should have a concave surface. So the posterior lens should have a concave surface in order not to have direct contact in the optics between the first lens and the second lens. So again, the dual optic accommodative IOL, by placing the two intraocular lenses inside the eye, this can now see the near and far targets, and the three designs are the dual flex, dual optic system, and the piggyback IOL. The second type of the intraocular lens is called the physiologically accommodative intraocular lens. And why it is mentioned physiologically? Because it acts like the normal process of accommodation. So by normal process of accommodation, there will be contraction of the ciliary muscle, and then contraction of the ciliary muscle will cause relaxation of the zonule. So there will be bulging of the lens. So by bulging of the lens, then will be an accommodation. It was found that in octopus, you know the octopus, the octopus see the near target by pushing his eye forward. So all his eye moves forward so that the octopus will see the near vision. And by using the same principle, the accommodative IOL have been invented. We will not push the whole eye, but we will just push the intraocular lens. So by designing a lens or this lens with this specifically designed haptics, when they are placed in the posterior chamber, when the person starts to accommodate and he will contract over his ciliary muscle, the anterior vitreous face will push the lens forward, so it will be moving in front of the lens. And then this intraocular lens now will be moving more forward, so its effective lens power will increase and leading to ability to see the near target. So it will act more or less like the physiological mechanism of accommodation that the normal person has. So this is the end of the intraocular lens. Do you have any question in the intraocular lenses? Okay, so let's move to the next topic, which is the laser.